What makes CppCon unique is it actually creates a nice environment to collaborate, to talk. They facilitate that people get together for networking. They don't just do presentations and that's it, but also arrange things outside the presentations.
Welcome everybody to my talk, Bridging the Gap, Writing Portable Programs for CPU and GPU. I have a little headache, so I will make strange facial expressions sometimes. So, I'm Thomas Mejstrik, I'm from University of Vienna. I'm actually a mathematician, but I worked quite some time at the company Demeter, and there I did a lot of CUDA programming, and problems we had there, and the solutions I'm going to present this talk. And my colleague Sebastian Woblestein, who is the co-author of this presentation, still works there. So I will start by explaining why it is interesting what I present here, why it is of use. Then I will show the problems and some solutions. At the end, I will make a very short proposal to the CUDA language, because I hope somebody from NVIDIA will see this. So, okay. You can ask questions anytime, also during the talk. I hope I repeat them, so everybody hears them. And I'm gonna start. Could everybody who is a CUDA developer raise their hands so that I know it? Yes, okay, that's good. And developers of other heterogeneous systems like OpenCL? Also some. Oh, more CUDA developers. Okay. This talk is only about CUDA, unfortunately. Somehow it got lost in the title. It's written in the abstract, but this talk is only about CUDA. So CUDA is an extension to the C++ language, and it allows to write programs for NVIDIA GPUs in a very straightforward way, nearly as easy as it is to write it for the CPU. And I don't know about OpenCL and so on, so don't ask me about it. I will not be able to answer you, but I'm happy to hear something after the talk. So the goal or the problem I'm presenting is you have a program which runs on the GPU, and you also want that it runs on the CPU. And you don't want to duplicate a lot of code, you don't want undefined behavior, you don't want a lot of boilerplate code. And you might think why this is actually a goal to achieve, because CPUs and GPUs are designed very differently. So they are designed to solve different problems. So an algorithm which runs fast on the GPU, it may be very slow on the CPU and vice versa. So usually you have an algorithm and all the parts which are fast in the GPU are offloaded to the GPU. So why would you want to do this? And because of this, I don't think a lot of people think about this actually. And I want to stress 4 points. These are the 4 points why we did this at Demeter. First, there are some algorithms where the best implementation on the CPU mimics the one on the GPU actually. So, for example, embarrassingly parallel algorithms. So, where you have nearly any communication between the threads and you parallelize them by just starting them multiple times, and then you have an n times increase in speed, hopefully. So, at Demeter, they compute where a drone can fly safely, so up in the air. So, for each point up in the air, they compute whether it's possible to fly there or not, which is perfectly embarrassingly parallel. But that was not the only motivation for us. The second was the user experience. In the beginning of the company, we had to motivate our customers to use our software, so our cell phone operators. And they were actually not willing to buy a GPU. So we had to make sure that we can show our program even if they do not have a GPU. But also for us developers, it was nice because we could run our program even if our computer did not have a GPU. So for example, on each possible laptop in the train, and we were not bound to our expensive workstation. And finally, debugging and testing is much easier if you can do it directly on the CPU. I tried to debug often on the GPU and I never make it run smoothly. So, in this talk, I will mostly talk about functions. I will not talk about how to organize your memory. This would be a totally different talk and would need totally 2 hours more. So only like containers, helper functions, manipulation, this kind of thing. I will not talk about performance. The goal is not that we have the one program which runs perfectly on the CPU too. The goal is we have a program which runs on the GPU, and we also want that it can be run CPU. And you will see we have mostly to navigate around CUDA problems actually to achieve this. Oh, sorry. No. Okay. Now, because not everybody here is a CUDA developer, here's a very short CUDA introduction. We will not need a lot of CUDA. Yeah. All you need to know for this talk is on this slide. And in CUDA, we have 3 types of functions. We have host functions. These run on the CPU. Host and CPU is quite synonyms in CUDA terminology. And the host functions are stored in the memory on the CPU. And then we have global and device functions. They run on the GPU, and they are stored in the memory of the GPU. So device and global functions can call device and global functions, and host functions can call host functions. Global functions are a little bit special because they are the entry point to start something on the GPU. But for this talk purpose, global functions behave as device functions. So I will not talk about global functions anymore, only about host and device functions. So here we have a very short concrete example, something like hello world, but without hello world. We have a device, global and host functions. These print, kernel, and start, and they are such functions because they are annotated with device, global, or host. Quite straightforward. And main in line 7 is not annotated. This means it's a host function implicitly. So in line 8, we would call our start function, which is a host function, which is nice. Main is a host function, the host function. Then we call here the kernel. It starts 2 times 3 threads. Each kernel prints 1 number, the number 0, which comes from the device function. Everything is nice. And then the kernel finishes somehow, and in line 9, we would wait until all kernels finish the computation, and CUDA device synchronize also takes care that the finally appears on the screen. So this is our code. If we want to execute it, we have to compile it first. There are 2 mainstream compilers, or not mainstream, most used compilers, I would say, NVCC and Clang. NVCC is not a full compiler in the sense that it always needs a host compiler. So NVCC does a 2-step compilation. It first takes only the device stuff, compiles it for the device, then passes it down to the host compiler, and the host compiler compiles for the host, typically GCC or Clang. But Clang can also be used as a standalone compiler. And I mention this because there are slightly different dialects in CUDA which they implemented, and we will see them later. There are also other compilers like HIP, AMD, and so on, but I will not talk about this. Now, this is if you run the program, 6 zeros in an arbitrary order because the kernels are running asynchronously. Okay, so now a quiz for you. Now you need everything for this talk, and here's a little quiz. The quiz is about, we have 4 function calls in line 9 to 12, and you can guess what happens. If you don't like quizzes, then stay very grumpy and don't raise your hands. But if you like quizzes, you can raise your hand. So we have a struct H and a struct D. The struct H is supposed to be used only on the host side and D only on the device side. And both implement the function func. And then we have a function rep in line 6, which is a template function. It's marked as host device, so it means it can run on the host and the device side. So we start easy. What do you think happens if we call h.func? Who thinks we get 42 back and no compiler message output? Yeah, this was easy. Okay. Now, what happens if you call d.func? This is a device function now. And I said it's not possible to call a device function from the host side. Who thinks we must get 666 and everything is nice? Nobody, that's good. Who thinks we have a compilation error? Ah, great, you are a great audience. Here is the error message, calling a device function from a host function is not allowed. Okay, now the interesting examples actually start. Here we call wrap and instantiate it with h. And the CUDA rules say if you have a template host device function, then, and we call it, then always the host and the device function is instantiated with the given type. This means if the compiler sees line 11, it implements, instantiates a function. Host int wrap, which returns h.func, and it also instantiates a function, device int wrap, which also returns h.func. Because int is a host function, the compiler in line 11 decides it calls the host version. So in line 11, we call the function host int wrap h.func. Who thinks no compiler output and at runtime we get 42? Nearly correct. With warning, correctly, it's a warning. The warning is about the compiler instantiated this device function. We never call it, but it got generated and the compiler warns us about this function, which if we would call it, would lead to bad stuff. Now, last case, we call wrap in the instantiate with d. So if in line 12, we call host int wrap, which calls d.func. Who thinks we have everything's okay? Who thinks compilation error? Unfortunately not. Who thinks compilation warning? Unfortunately not. The answer is we have no warning, but undefined behavior at runtime. Okay. So this was tested with NVCC 12.6, and I sent this example to NVIDIA a long time ago, and they told me it's fixed in the next NVCC version, but I don't know which is the next NVCC version. So yeah, I think writing compilers is hard, so I don't blame them. But we hope that this strange behavior between line 11 and 12, I hope at least that it will be fixed soon. Currently, we have to deal with this. So, and if you compile with Clang only, actually, I don't know what happens. I tried it and I had no warnings and errors for all of 40 examples, which is at least consistent. But the Clang documentation says this is also line 12 and line 10, both is a compilation error, which I could not reproduce, so I don't know. Okay, now we come to the problems and the solutions we had at Demeter to solve a task. First solution is not really feasible because you could use a really old CUDA version. I don't know how old, I could not figure it out again. I think CUDA 2. And in this old CUDA version, there was a compatibility layer implemented so you could run CUDA code on the CPU without problems, but NVIDIA removed this. So this is, unless you're a masochistic, this is not the solution. So we start with more feasible things. So first pattern, host device, all the things. It's very easy, so I just show you the problem and the solution. We have here this function megahertz to wavelengths. Give them a frequency in megahertz, it returns the wavelengths. And this function currently only works on the host side, and if you want to make it work on the device side, we write host device in front of it and we're done. Perfect. So, if this is a valid solution, this is the way to go. But it's not always nice because this now would be the code of our quiz. I added host device everywhere, and now we have two not so nice things. First, code bloat, so binary size is bigger and compilation time is higher. Second is, I said that the struct H was something like a host-only type and D was a device-only type. But now we can use both types on both sides. And so we hide logical errors maybe. So if you have really host-only or device-only side, you should not use this. Oh, I think, yes, I said everything. Now, next idea. I said we wanted to be able, in the motivation part, I said we wanted to be able to develop everywhere, even if you do not have a GPU at hand. And if you have no GPU, we most likely have no CUDA capable compiler, because cross-compiling is not so nice. So we wanted to make sure that even such CUDA-looking code compiles with GCC. And of course, if you compile something like this, we have an error because host is not known to GCC. So what we did is the following. 41 minutes, okay. We just checked whether we are compiling with a CUDA-capable compiler by checking the macro CUDA-cc. And if it's not defined, we know the compiler doesn't understand, so we define these macros to nothing. And now this perfect compiles perfectly. Who sees this problem with this solution? This is undefined behavior, because you must not define identifier starting with an underscore in global namespace, so you're not allowed to do this. Yet we did this, and I don't think it will ever make a problem, because first, the GCC and Clang writers, they know host device, these names are taken, and then there's so much legacy code out there which it makes identifiers starting with an underscore, so they will not harm you. Of course, if you don't want undefined behavior, you have to do something more evolved like this. So you have to define your own identifiers. But then you have to tell all your colleagues, use this hostname-f macros. Yeah. Okay, next pattern. In the example at the beginning, we had this frequency to wavelengths to frequency macro function. And there we had one function body which was usable on both sides. So the implementation was, I guess, the best implementation for CPU and GPU. But if you have a function which is where the function body is not usable on both sides because you use intrinsics or you want to have different implementations, you have to do something about this. And of course, you just check some pre-compiler macros to do this. But there are some caveats now here. So at Demeter, we had, for example, this with, we had to compute the true norm of a vector, and then the host side we did it manually, and in CUDA there's an intrinsic norm 3df. So how can you achieve a conditional function body? I said there are two compilers mainly used, NVCC and Clang, and they speak different languages, slightly different CUDA languages. First, also one difference is that host device annotation is part of the function signature for Clang, but not for NVCC. This means in Clang you can overload with respect to host device, but not in NVCC. But NVCC has this two-step compilation thing, first device code, then host code, and you can track in which step you are by checking this CUDA arg macro. CUDA arg is exactly defined as compiled. There are some restrictions how you can use them, which may make problems, but I hope not. And NVCC is this is a macro where to check whether you compile this Clang or NVCC, but I never needed it actually. So I skip this. So for example, the norm function to compute this norm of vector would look like this. In the host side, we do it manually, and the device side, we call norm 3df. The double thing in the norm function is because of numerical stability problems we had. And in NVCC, we check whether CUDA arg is defined, and if not, we do it manually. If it's defined, we can use the intrinsic. So I would always use actually the NVCC version because Clang also understands the CUDA arg macro, so the right-hand side is portable. The left-hand side is not portable. Now to the restrictions to CUDA arg. I quote from the documentation. The signature of functions, function templates, and instantiated function templates, as well as the arguments used instantiate function templates, must not depend on whether CUDA arg is defined or not. So this means all the compile time typey stuff must not depend on CUDA arg. And I don't know if the same applies to if const expression or not. I wrote an email to NVIDIA, but they did not reply to me. So maybe somebody here can tell me afterwards. Okay, this means what comes now next is not a solution. And this would be the code from the very beginning, actually, where we called rep-h with the compiler warning. And here, rep-h would only be instantiated if CUDA is not defined. But this is a violation of this quote, so this is not a possible solution. But we have a small problem. If you really have if you really are in this situation where you have a host type and a device type, and you want a function which has some on the host side returns the host type, and on the device side you have the device side. You can do it in Clang because you can overload with respect to host and device. In NVCC, actually you cannot do this because then the function signature would depend on CUDA. The strange thing is on the Clang documentation page, they give this code example here on the right side, NVCC. This would be a pattern. They say this would be a pattern to solve this, but actually this is also undefined behavior. So I don't know whether you can do this actually in NVCC or not. But I think if you have a function where the signature depends on host or device, then you have you should rethink your software design actually. So next pattern, very similar to the one we had. Const expression everything. Okay. Here, again, we have a function, and it's a const expression function, and you see we use std array and some algorithms from the standard library. And we want to be able to compile it with NVCC. And also we want to use it on the device side. If you compile it now, then we get this error calling a host function is not allowed. Also calling a host from a device function is not allowed. Std array is, of course, host only. Now, but the compiler is nice and says the experimental flag, experimental relaxed const expression can be used to allow this. And if you pass this flag, then the compiler considers each const expression function as a host device function. And there are even 2 talks on YouTube, and actually all they say is use this pattern and all your problems are solved, but the thing is it's not that easy, actually. So the first thing is experimental relaxed const expression works only on NVCC. So if you use this, then you're bound to NVCC. Second, it's experimental, and we will see some problems with this. And one indication that it makes some slight problems is that there's a library by NVIDIA, Rapid, and they discussed whether they should use this, and then they decided. There's another library by NVIDIA, and they also discussed whether they use it, and they happily take it. And at the meta, we didn't use it, and we thought it's a good idea, and then we found maybe not. And here are some examples what can fail. So a const expression function is allowed to throw as long as it does not throw during compile. But a device function is never allowed to throw because exceptions are not supported on the device. So if you have this function foo and you compile it with NVCC, then the compiler changes this function to unconditionally returning 42. Not even some warning or something. This is a similar example here. We have an example where a const expression function calls a non-const expression function. This is okay for the CPU, but of course not for the device side. Because on the device side, then the device function would call a host function. And he silently changes this function to returning 42. So you silently introduce the bug, actually, without even noticing it. Here's some other example. Here we have a const expression function which does a transient memory allocation. And this may work or may not work. It depends on your graphic card's operating system, graphic card driver, I don't know what else. But even if you have total control over your system, it's probably nothing want to happen actually, because on the GPU, everything runs in parallel. That's why I use it. And now if the GPU comes to line 2, then all of your threads, thousands hopefully, do a dynamic memory allocation at the same time. So this is probably not good for your performance. So let's sum it up. The great thing is you can, if you use this flag, experimental relaxed Constexpr, then you can use big parts of the C++ standard library without any further ado, because most of a lot of functions are marked Constexpr. But you could silently introduce bugs without even noticing it. At the Meta, a colleague 2 weeks ago, I could not look into the exact code, but he told me they had a Constexpr function, they used it, and then it was compiled wrongly, and when they changed it to host device, it was compiled correctly. So there's also seem to be some compiler bugs still there. Okay, and yeah, of course, you should not use this in a library, of course, because then your users are forced to use experimental features. That's also nice. So takeaway here is carefully think about whether it's worth the hassle to use experimental relaxed Constexpr. So, any questions actually so far or not? So, no, okay. Then, next way to do, next pattern. So, you have a program and it emits warnings, and you know the warnings are wrong, so you just disable them. So, for example, here we have some algorithm, fill once. It just takes a container and writes once into the whole container. This is some not production rate, also not real code, but you can imagine the application would be some algorithms. And if you now call it from the main function, then we get this warning because this fill once is a host device function, and this host device function then calls a host only function. Who sees which function is called? Which host only function? Yeah? Yes. So, but we are very clever developers. We know the code is correct, so we decide we just disable the warning because the compiler gives us a false warning. And we can do this, for example, with this pragma, and we exec check disable. But and the exec check disable works in the following way. So, if you apply this, if you write it in front of a function, and this function makes a bad cross function call, then you don't get a compiler warning. If the called function would make a bad cross function call, you have a compiler warning, so it's not recursively. HD warning disable actually does the same. Both pragmas are undocumented. Sometimes one works, sometimes the other, sometimes both, sometimes none. So actually it's strange. And on the CUDA forum, there is a discussion. Somebody found an example where the usage of nvexeccheck disable led to a wrongly compiled code even. So it's not clear whether we should use this pragma or not. NVIDIA uses it heavily in their Rust library yet, still. Okay, there are also other ways to disable warnings. These push pop-like things like we have in GCC and Clang, where you can disable warnings specifically for certain lines. Then you can disable them globally. And of course, you can also mark every function with Constexpr or host device. This is also a way somehow to get rid of the warnings. And as I said, Rust uses this pattern. So Rust is something like a standard library for CUDA. They implement a lot of CUDA containers. Also, the containers for the GPU and algorithms. And they mark all the algorithms with nvexeccheck disable. And I would not recommend this to do, because then the user has to check whether everything is okay. In my opinion, lower bound should be a black box. I give it something to work, and then I get some result. But here, if I use this, if it is warning, now I have to go into the interior of this function. I have to check which functions are called, which functions must be device functions, which functions suffices to be host functions, for example. So the user then is forced to look into this third-party code. In Eigen, this linear algebra library, famous one, also uses this, and also they use experimental relaxed Constexpr, so they do Constexpr all the things thingy. And at Dimeto we also do the same thing because we could not find any other way how to get rid of these false compiler warnings. At Dimeto we decided actually we do not use Eigen in CUDA code at all, so this is now safe but in Dimeto. But of course, if somebody else in the future doesn't think about it and then again uses Eigen in CUDA code, we would have a problem. So summing up, I forgot one thing here, the future to say. So I said in this example, at the beginning it was, so we had this call to this fill once function. We knew we only call it from host side, so the compiler warning is wrong. And we disable the compiler warning. But if somebody refactors the code or it gets changed, and suddenly we call it from the device side too, then we do not have a compiler warning anymore. So the compiler doesn't warn us. So I would not recommend to use this, but sometimes it seems to be needed. Next one. Oh, yeah, I'm quite fast. Host device. This is actually not the pattern because all the stuff I showed you before is used in industry by a lot of people. And this thing is invented by me. So I think Dimeto is the only one who uses it. So it's not strictly a pattern, but I still call it like this. And we are still here with this example. So we have this fill once function and we call it from the host side. Yet the compiler does not know. We only call it from the host side, so we have this wrong compiler warning. And then we can do some macro trickery and everything is solved. So this is now a little bit more code than before, so we make it a little bit slower here. You can use this pattern when you're in the situation that you can, if you can encode the target, so the site for which you want to instantiate your function, into the types. So the types carry the information where you want to instantiate your function. And the solution now is we overload actually with respect to host device and host device and make it such that the compiler chooses the correct version. Of course, in NVCC, we cannot overload with respect to host and device, so we have to do some requires trickery. And this is how we did it. So first, we have this enum HDC for host device compatibility. And HDC has a member host device and host device. So the identifiers are so short, so they fit on the screen. And then we have 3 times exactly the same function. So same function body, same function name. Only difference is once it's a host, once it's a device, and once it's a host device function. And it's a template function, so it takes a t, and additionally it takes a second argument, which is defaulted. And it's defaulted to get the value of lowercase HDC. And lowercase HDC is just the helper functions. It inspects the type and gives back for which side you shall instantiate it. And now, everything which is missing is the host function requires that x evaluates to HDC host, and the device function requires that little x evaluates to HDC def, and the host device function x evaluates to host def. And so for the developer, it's quite some code to write, but I think it's reasonable code. You can figure out what's happening. It's not too complicated. So I think it's okay. Nice thing is for the user, it's very straightforward to use. So the user just calls the function func with some t, and the compiler figures then out which function to instantiate, and we cannot have any bad cross-function calls because the function is only instantiated for the correct side. Even more, actually, if we would call a host-only function, for example, here in line 2, we have this fill once function, and we call it with this host-only type. Then, if we would call this, we would get a compilation error, because The compiler figures out, we call here we are in a global function, and we call a device-only function. And in this case, we saw the very beginning, where we had only device, and we did not went over this host device template thing. In the quiz time, we saw that in this case, the compiler figures out that this is wrong, and it gives us a compilation error. So the same, if we call the device function fill once from a host function main, then we also get a compilation error. So perfectly nice, except that now we have a lot of code application, of course. And we can get rid of the code application by introducing a macro. So this macro just generates all this code, and then fill once. This function is also, it's quite easy to use. So you give in line 13 to 16, you give the template arguments, you write down the function which tells you for which side you want to instantiate, and the function body, the whole definition. So, but this now makes a small problem, and the problem is if somebody has a good view, it's hidden in this slide, the problem actually. Yeah, here I wanted to say, here you can see how this helper trait actually works, or how we did it implement. So this lowercase HTC inspects a class whether there exists a member variable HTC. And if so, then it returns this value, and if not, it returns host. And if it's some type like int, float, or something, it returns hostdef. And here is the problem we have. Here I have a bug. It's an off by one bug. You see, operator square brackets returns index +1. Okay, this is a stupid bug, but I wanted to introduce a bug here. And at the middle, in the code base, I had a similar bug. Not this one, it was a different one. But I called this function something like fill once, some algorithm, and the result was wrong. And then I looked at the function body of fill once, and I saw it must be correct. I knew it must be correct because I copied the code from CPP reference. So I knew the code is correct. And I was wondering, why is the result wrong? And the reason is, the bug was not in the fill once function, but in some function which got called. But because the function body is in the macro now, I couldn't debug it actually. So I had to expand my macro, manually recompile, then I could debug. Then I saw, oh, it's jumping in here, I have here the bug, and then I had removed the macro, also made it to a macro again. So also this host device template pattern actually solves all the problems. We have no bad cross-function calls. We have compilation errors. If somebody goes wrong, it's not nice because you cannot debug well anymore. So it's not perfect. And so I sat down. Now something comes which unfortunately did not work out, but I still want to present it actually. So I sat down in my room and I was crying, and I thought I must be able to find a solution, and I call it the function dispatch triple. So don't do this at home, or don't do this. I show you parts of the code which results there. Okay, the idea is now, like every time in computer science, every problem can be solved by an additional layer of indirection. So we use this triplet template idea from before, but we do not call our fill once function directly, but we call a dispatching function. And the dispatching function then calls our fill once function. Now the fill once function is again, also the function we want to call, is again a host device function. So we have a host device function which calls a host or device or host device function, and one of these three functions again calls a host device function. And then in this host device function we call other functions. So we get again warnings because now we have again a call from a host device function to a host function, for example, like we had. But now we can disable the CUDA warnings because we cannot have a bad cross-function call anymore. Because if we would have one at the second step, we would already had one at the first step. So that's not possible, so we can safely disable them. But You can imagine this is even more boilerplate code, even more code application to before, so you really even don't want to write this as end, so you must use a macro. Then you have problems with parentheses and commas and empty macro parameters, and then we were bound to C++17 because CUDA lags behind a little bit, and we could not use C++24, so requires we could not use, we had to use std enable if. And so this is part of the macro. Actually, it's 10 macros which work together. And so it's not understandable anymore what happens here. And then if you want to write a function, you have to write the boilerplate code in the lower box, line 1 to 10. So that's also not nice. So also it solves the problem. It's way too complicated. It's not maintainable, so don't do it. I present it because I still have the feeling that it should be able to make it a better implementation of this idea. Because the idea is nice, you just do this, use this template. So you overload with host and device, and then you can disable the warnings. But it doesn't work out, unfortunately. So now, last part, 2 proposals to the CUDA language to solve these problems, some of the problems in a nice way. So first, conditional host device. And it would be great if host and device accept a bool like we have it in explicit in C++. And so if host of something is true, then it's a host function. If device of something is true, it's a device function. If it's false, it's not a device function. So this would nearly solve all the problems I showed you. This would be a pure language extension, so it would not break any code because this syntax is not allowed today. Very easy to use, and you could perfectly define where you want to instantiate something. And this means we could make all bad cross-function calls, so all calls the host function from a host device function, for example, to a compilation error. We saw in the quiz in VCC, the compiler does some special casing. Template functions were obviously differently treated than non-template functions. So if we could say exactly where we want to instantiate, we could make everything to a compilation error, and everything would be much more nicer. So that's it. I was way too fast. And the paper where everything is nicely written and in more detail can be found on the archive, and the slides in a few days on tomsch.com. So thank you, and ask questions if you have some.
Hi, good talk.
Oh, thank you.
Yeah, how do I say this? When I look at the way that you're using host device, it feels like the how do I say? Oh, okay, I'll back up a little. To me, the idea of a host device function is that it's portable. And so if I have a function called fill_ones and I mark it as host device, and it's templated on a container type, and I instantiate it with std vector, I've already made a mistake. Like, because I've taken a thing that's a host-only thing, and I've given it to a host device function. The essence of host device function is it is portable. Like, it can be run on this side, it can be run on that side.
Yes.
So if I give it a std vector, I've kind of already lied about the portability of my code, because now I've instantiated a generic portable function with something that's not portable. And so I feel like I don't write code like that has all this different dispatching based on host or device, and I would never want a function that returns different types, whether it's host or device.
Yeah, that I also will never do.
So yeah, it's a little strange to me, the idiom. So I'd like to learn more about what you're trying to do.
I think the example I gave, we used fill_ones and they called it on the host side. So if you're a library writer, for example, Eigen, in Eigen you can use on CUDA, or you should be able to use on CUDA. So everything is marked as host device, but also people want to use it only on the CPU. So people who have no NVCC also want to use it, but they marked everything as host device. So if you compile it now with NVCC, you get tons of compiler warnings because you used your eigenfunction on the host side, but it's marked as host device. You were never intended, you never thought about this, I want to use this on the GPU side, but you still get the compiler warnings. So if you write a library and you want that CPU only people can use it, but also CPU and TPU people, you have a problem. That's not possible without compiler warnings.
I want to talk more about that sometime, but
Okay.
Also you forgot a compiler, NVC++.
I meant NVCC with NVCC.
No. A compiler called NVC++, which is not NVC.
Also, NVC++, yes.
Yes, don't forget that one.
Yeah. there were 3 dots.
Yes.
Yeah.
So regarding the relaxed const expressions, so it works fine if you're really, really disciplined. So if you initialize any variable you use, and if you take the utmost care not to call anything that's not const expression, it works. But I give you that the compiler fails silently and the code fails silently if you don't do this, but not always.
The problem is, if you have a third-party library and you think about, I want to use it in CUDA, everything is const expression, I use this flag, you don't know whether the third-party library, they were disciplined or not.
No, you don't. So you can only use it in places where you can
Yes.
control what's called.
Any more questions? Then thank you for listening and have a long break now.